Welcome to the new episode of Pe Charcha. Pe Charcha is an initiative of VLSI Society of India where we bring the global technology leaders of the semiconductors, and in today's episode of Pe Charcha we have Professor Umesh Mishra, known as Guru of GaN. Welcome, Professor Mishra.
Thank you very much for having me.
So, in today's episode, we are going to focus on the compound semiconductor, which is a very fast emerging field of the overall semiconductor ecosystem. So, Professor Mishra, first of all, we want to start with your early days. You grew up in Delhi and Pune regions of India. So, just share with us how was your growing up, how did you get interested in the science and the technology?
Well, thank you again, Satya, for having me. This is a real honor to be to speak with you today. I think that my growing up in India was, as far as technology was concerned, was greatly influenced by my father, who actually was in the Ministry of Defense in India, and I grew up born in Pune, went to school in Bangalore, and then also in Delhi, and then finally ended up in IIT Kanpur. Now, my father was very deeply interested in microwaves. He was the director of solid state physics lab. So because of that, I got interested in semiconductors from high school, and did experiments for my science talent project in SSPL. So I'm one of those strange people who got interested in semiconductors very early, and then of course under the tutelage of great professors in IIT Kanpur, Professor Sharan, Professor Tyagi, and most importantly Professor Shamresh Kar, who passed away recently. I kind of honed my skills. Yeah.
So after you graduated from IIT Kanpur, you decided to pursue your higher studies, and how did you get into the field of compound semiconductor and when you started basically in this area?
So it's very interesting. I went to school first, got my master's from Lehigh University in Bethlehem, Pennsylvania. I was working on silicon dioxide system under Professor John Simmons, who then left and went back to England. At that time, I had an option, either go to the UK with Jack or change my field. At that time, which is 1980, the whole concept of ballistic transport in semiconductors was coming up. The way to model electrons transiting very small regions. This was very exciting. And so I thought that, and the center of that activity in the US was Cornell University. So at that time I decided to basically change out of silicon into compound semiconductors, and I joined Cornell under Professor Eastman. Yeah.
So for some of the people who are new to compound semiconductor, can you very briefly explain what are those compound semiconductors and what is the evolution of basically technologies like GaN and Silicon Carbide?
So yeah, great question. As opposed to silicon, which is an elemental semiconductor, compound semiconductors are made out of, as the name suggests, made out of two or more elements. And so gallium arsenide and indium phosphide are the two famous semiconductors in the past, and they are the backbone of the optical industry. So telecom lasers are made out of gallium indium arsenide materials, which are grown on indium phosphide substrates, and gallium arsenide based VCSELs are in the camera of mobile phones like Apple, iPhone, and so on and so forth. So compound semiconductors are not in computation, but they are everything around computation. However, now compound semiconductors are entering computation through silicon photonics, through the chip board-to-board interconnects, and also many other such interconnector opportunities. After gallium arsenide, the next big semiconductors that came out, which are compounds, were gallium nitride and silicon carbide. And this has basically really been the story of the current decade. And I think it's going to be the story of decades to come, because it is going to be the engine for electric vehicles going forward, the next generation of photovoltaic inverters, power supplies for data servers, adapters, and so on and so forth. So the UPS systems. So it's just going to impact the full power conversion and, very importantly, also for India, the RF domain in 5G and the new radios coming up after that.
So you are one of the pioneers basically which made GaN from basically research topic to a commercial entity, and you must have a lot of fellow travelers in that path. So can you just walk us through last 15 years of evolution of technologies like GaN?
Sure. The aluminum gallium nitride HEMT, which is the backbone of gallium nitride technology, was invented by Professor Asif Khan, who is now at the University of South Carolina. And the other big, and around the same, in 1993 or so, Professor Shuji Nakamura, my colleague at UC Santa Barbara, actually developed, while he was still in Japan, the blue LED, which is the basis of white lighting. Professor Nakamura, with his colleagues, are not the co-inventors in a different institutions, mainly Nagoya University, Professor Akasaki and Amano. Together, the three of them got the Nobel Prize in Physics in 2014 for the development of gallium nitride-based LEDs. So gallium nitride-based semiconductors was the big boost came from LEDs. But then now is the era of not only photonics and gallium nitride, but electronics. Fellow travelers would be in the US, say major aerospace corporations and DoD contractors like, say, Raytheon, which has played a big role in transitioning gallium nitride to military assets like radars and so on and so forth. Others like Northrop Grumman have done so as well, and in the electronic warfare area, people like British Aerosystems, BAE. Now, in the commercial space, there have been many people. I mean, I'm just drawing broad contrasts. It's not clear divisions, but Qorvo in the US, Wolfspeed, and in Japan, SEDI, Sumitomo Electron Device Innovation. These are the big players in deploying gallium nitride in 5G RF. So, of course, I've been blessed to be able to give them the opportunity to contribute to the commercialization of gallium nitride. But of course, like you said, every journey has fellow travelers, otherwise it's a very lonely journey. Yeah.
So, about 15 odd years back, you decided to do your basically own manufacturing of gallium nitride devices through a company called Transform, you was co-founder.
Yeah.
So just basically take us through ups and downs you had to go through in the last 15 years of basically very nascent stage of the gallium nitride for power electronics, and how you have come so far in this, and what does hold future for the Transform?
Thank you for the question. Transform has been an amazing journey, and to me it's been probably the most difficult journey of my life, and also with the potential of the biggest rewards. Primit Parikh and I, an alumnus of IIT Kanpur, IIT Bombay. I'm from IIT Kanpur, he's from IIT Bombay. And then he was a graduate student of mine at UC Santa Barbara. We co-founded Transform in 2007 with the idea of taking gallium nitride and actually making it a real product in the power conversion space. Now, to go from PowerPoint to actual product is a long journey, and the journey is pretty unique, but the basic And each semiconductor and each company has their own experiences. But what's cross-cutting amongst all of this is it takes longer and it costs more money than you ever imagined. And so what you need to do is to basically stick with it if the vision is correct. And you got to actually, the vision has to be so strong because you have to raise so much money from so many people that the vision should not tire while you're trying to raise the money, because it'll take a lot. So we realized that, first of all, when you're not trying to actually enter a market where there's a void. So for example, take the LED. The LED fulfilled a need where there was no solution, like the blue light. Nothing put out blue light. So when something with blue light came, people accepted it with a very low bar of acceptance. In power conversion, we are trying to actually compete against silicon. And it's, that's the mother of all materials. So you're basically trying, so what ends up happening is that you have to have the performance which is much better than silicon with a cost target which is close to silicon. This is a heavy burden to bear. And what you have to do therefore is to improve everything. Have the best possible material, the best possible processes, the highest possible yield, because the 10% loss in yield is a 10% increase in price. So you have to have a highest increase, you have to have a high yield with a very high reliability. And so we worked very hard and we put money into growth of the gallium nitride. We have chosen to grow on silicon. The device design, because there are many ways of making GaN HEMTs, and we made the cascode normally off device as our product of choice. And then we basically took over the Fujitsu gallium nitride power business, which allowed us to make the devices in a very high-end fab, not a high-end as in very modern, but high-end as in very disciplined and a very well-run factory in Aizu, Wakamatsu. So the ups and downs are one that every business faces. Everything you think is going to work is not going to work until you make it work. And that can take inordinate amount of time.
Technically, what has been your biggest challenge in basically creating a commercially viable product for power electronics through your efforts in transform for GaN? Technically, what has been most challenging?
What has been most challenging has been the fact that you want to make sure that this technology becomes a highly repeatable technology. Gallium nitride is a heteroepitaxial technology. There's no gallium nitride substrate which is of low cost. It exists, but it's very expensive. And this technology has to serve a very large market. So silicon was a natural substrate. Now Transform is also doing gallium nitride on sapphire for very high voltage devices, like 1200 volt devices. But if you look at us, the most important thing for us was to get the epitaxy right. That took a long time. And then we had to make sure that the process was reproducible and highly reliable to be automotive qualified. That took a long time. So it is, and the interaction between the device and the material is complex. So of course, since we own the full supply chain, changes in the material and its impact in device design, we control. So we basically, we could actually do it most efficiently, but not efficient enough,
So it seems like in last 3 to 4 years, the compound semiconductor for power electronics are kind of coming out of the age. And we see a lot of action in the global landscape in terms of acquisition, consolidation, and so on and so forth. So how do you see that basically current landscape, global landscape of compound semiconductor is shaping up? What are the basically forward-looking potential to many big guys getting into it and significant mergers and acquisitions?
So compound semiconductors, compound semiconductor big thrust areas are silicon photonics. That is going to be huge. It is huge, it's going to get bigger because copper as an interconnect is reaching its limits and silicon photonics is going to be it. There actually gallium nitride is also playing a role where free space interconnects due to gallium nitride blue LEDs is being able to give you terabit per second kind of communications multiplexed over many LEDs over short distances. Over long distances, people are still using telecom lasers. That's a big, big, big market. In the wide band gaps, I think there's huge excitement. Silicon Carbide was dormant for a long time until Tesla decided to use it in their automobile. Then the fortunes of Silicon Carbide flipped for the better. And then, so that's growing at a blistering pace for two reasons. Silicon Carbide was adopted first because it has a very long history and it is perceived as being more mature, and it is. But, and then it was perceived to be the only wide band gap semiconductor that could do 1200 volts. That has changed. Gallium nitride now is, the price has dropped of gallium nitride. It's become more widely available, multiple sources of transistors. So now it's also become very widely accepted in the marketplace. And in the low power sector, less than 1 kilowatt, silicon carbide cannot compete anyway. It's not appropriate. But you end up, I believe, that there's a golden age of compound semiconductors. Silicon photonics to power up the computing industry with the expansion of computing in the cloud and so on and so forth. A lot of quantum computing is going to be done in the future with compounds, and there is going to, and then of course the whole revolution of gallium nitride and silicon carbide. It's going to be a blistering growth in the next, I would say, 2 decades. It's exciting times.
Okay. So, there has been some major acquisitions in this field, basically for in last 1 year or so.
Yes.
Infineon buying the GaN system,
Yes.
and basically Bosch buying a fab, TIS fab for $1.3 billion.
In California.
And California and many other such things.
Mhm.
So, how do you see this basically playing out in the field?
Very good question. So what is, this typically happens. So basically, right now I think silicon carbide consolidation has been going on for a long time actually. Fairchild bought a company in Sweden. That's how they got silicon carbide in-house, right? Rome Corporation bought SiCrystal, and so on and so forth, brought bulk silicon carbide in-house. Infineon has bought companies that do smart cut of silicon carbide, and so on and so forth, to make thinner silicon carbide. So there's a lot of consolidation. Gallium nitride, the consolidation is just beginning because there is this Infineon buying GaN systems was the first official market-driven validation of GaN and its potential. So I think there's going to be a consolidation that will happen, and there'll be an expansion of capacity that will be needed. Because people buying GaN systems, Infineon buying GaN, this is just my opinion, Infineon buying GaN systems for $800 and some million, you don't do that unless you want to sell a lot of chips. So basically there's going to be a need for more capacity in the future, golden opportunity for India, for example, and also in the US and other places.
Sure. So that directly segue into my next question to you. What is India's opportunity in compound semiconductor, especially looking at the power electronics area, right? Lot of basically potential growth in EV and other sectors. So how do you see this global capacity expansion for India to basically play to the domestic need as well as basically global demand of the compound semiconductors?
India is uniquely positioned. Why? Because the Indian EV market is actually composed of two very large segments, the four-wheeler market and the two and three-wheeler market. And the two and three-wheeler market, India is already the export engine for the world. So it's not like, oh, India has to penetrate global markets. India is the supplier to global markets. So let's start with the two and three-wheelers. There is of course, there are so many companies in the US, in India, both new and old companies switching to EV. These are vehicles that need onboard chargers. They need drivetrains. For the onboard chargers, I think gallium nitride is uniquely suited, and the reason is that the power levels there and the need for extreme efficiency to shrink the size. This two-wheeler, three-wheeler doesn't have much room to carry an onboard charger. So their space is a premium, efficiency is max, the demand is high, and the cost has to be low. And so that means gallium nitride is going to penetrate that in a big way. I'm 100% sure of that. Onboard chargers are also going to be a big deal in four-wheelers of all types, right from the small four-wheelers all the way to, I believe, even cars of the size of Tesla and Lucid and so on and so forth, 400 plus kilowatt. And I think that in my mind, if one ends up looking at the opportunities that we have in India for doing gallium nitride products, not only manufacturing. I know you have been pushing this narrative, Satya, of India being a product nation. This is something you've been talking about. And I think that I agree with you. I think that the products that are where India can play in the EV sector is just, it's an open book. Now, once those products are made, not necessarily in serial order, but definitely at least in tandem, then you'll develop a huge pull to make the chips in India as well. So I think that there, because we need to, but there's an issue with this, and we can talk about it later. If we had enough of a workforce, and workforce training is very important, the chip sector for power electronics in India, in my mind, is the low-hanging fruit. Of course, India should be in silicon, and they should be doing 28 nanometers, whatever, and less. And that's something I'm not very, I'm not an expert in, but I know that India should do it. However, I know for sure that power electronics, power conversion, and RF, using gallium nitride and also silicon carbide, but I can say for sure gallium nitride is something India is right to do and should move forward as quickly as possible. I think delay of doing things in India is inexcusable in my mind, because if you miss opportunities, you not only miss the opportunity, you miss the market. And I think that people should be a little bit, should not be so risk averse. They should just take the risk. Risk always has the potential of something going wrong, but without risk, there's no reward. Yeah.
That's why it's called risk, right?
Yeah, that's right.
So everybody basically, when we talk about compound semiconductor, talks about EV. But India has a very diverse portfolio of power electronics devices. So can you shed the light on what other areas basically India is uniquely positioned to take advantage of technology like GaN and Silicon Carbide?
Oh yes. For example, for me, the big one is solar inverters, micro inverters behind panels. We are transformed. We are the only company in the world that actually is deployed in micro inverters. Okay, and for that, microinverters need to be efficient and need to be capable of handling high temperatures, because it's up there, the sun is beating on the panel and everything is hot. And we are in the market today, so there's no question about gallium nitride's reliability under those circumstances. And the microinverter is small and highly efficient. That's number one. Number two, air conditioning. The demand for air conditioning in India is going to go up. And the drive for air conditioners have to become smaller and more efficient. Water pumps have to be small and efficient, and that's where gallium nitride can play a role. You look at data server power supplies. Data servers are going to boom in India. Computing at the edge. That's also going to, every place where you are space constrained, you will need to do this. 5G towers, the power supply has to be GaN and the transmitter has to be GaN. So I think that if you look going all the way through, and I'll finish with one particular area that I find very interesting is UPS. If you look at, the power grid in India is not 100% reliable as far as delivering power at all times, but you end up with, if you have a UPS system, you can ride it through, and their UPS system, and this is not for homes I'm talking about, this is for industrial sector.
But is it useful for home also?
Absolutely, because if you make an industrial UPS system which is fully deployed, then you will end up with the ability to make effectively the equivalent of like Tesla's Powerwall. And then you can actually have and I'm just using their terminology, I don't mean to say it's exactly that, but you can make effectively a Powerwall with GaN as the inverter driver.
So you must have seen India's new semiconductor policy,
Yes.
also India's semiconductor mission.
Yes.
And considering the importance of compound semiconductor, the initial incentive of the 30% was raised to 50% in the revision of the policy about basically 6 to 8 months later. How do you see these incentives provided under the India Semiconductor Mission, not just incentive, the overall 360-degree nature of the policy? How is it going to enable making more compound semiconductor-based products? I just don't mean to say fab alone, but making compound semiconductor-based product to satisfy the both power electronics as well as the RF needs of the country.
It's a great policy. I think that with the government central government putting in 50%, and the states also being very aggressive in helping out, this could actually, this de-risks the deployment of capital significantly. I think the private sector has to step it up now and basically actually be willing to take even the reduced risk that is there. They have to definitely take that up, and we see indications that the private sector is stepping up, which is a good sign. I think that the most important thing there is technology has to be, India doesn't have the time to develop the technology from scratch. I think we should, and I think this is something you and I have talked about, the need to separate research and development. I think it's not necessary for India to actually develop gallium nitride from scratch. That's not necessary. I think what India needs more than anything is to develop products using GaN and basically seeing what's the best way to jumpstart the gallium nitride effort in the fab, rather than trying to develop it from scratch. Indigenous developments of the technology will happen organically, but there's no reason to spend all your effort trying to develop something indigenously if there's no products. So I believe then the mission should also incentivize products, not only fab. And if they do that, if they broaden the scope of this a little bit more into design and products, then I think that it'll jumpstart the process within India. RF is a separate matter. RF is more niche, and and also there are export import control issues in RF, and there India may have to step up and try to develop its own gallium nitride technologies or get it from some friendly nations. But at the present time, I think that power conversion is something that India can really jump into. Yeah.
So, I think you touched a little bit about the talent part.
Yeah.
Right? So, India and US basically share a very broad highway in terms of basically students
Yes.
going to US and basically
Absolutely.
getting trained and so on and so forth. So, how do we leverage this relationship to develop the world-class talent in semiconductor, which will benefit both US and India, because both the countries are going to need this talent in the huge quantities in the coming year. So what are the efforts we can take on to basically build more deeper relationship in developing this talent, which will serve the rest of the world?
Very good question, very tough question also, because it's a multifaceted question. One area is what I would consider to be the development of technical talent. By that I mean there are levels of technical talent. There's how do you train operators, okay, and technicians and so on and so forth. That's an important role to play, right? And that has to be done relatively locally, right? Then there is the actual training of the interaction between understanding how to design the product and actually manufacture it. I believe I think we should have an agreed upon curriculum which can be delivered by the United States professors. I'm interested in doing that at UC Santa Barbara. I'm going to be taking over as dean and of the University of Santa Barbara College of Engineering. And one of the things that I'd like to really get into is try to deliver education online for matters which are of importance to both. For example, you brought up the joint interests of India and the US, but semiconductors is a classic example of joint interest. So I think having curricula that actually help train people rapidly by people who are actually experienced, not only what I would call pure academics, but people who are academics but have also practiced in industry. I think that curriculum would be a much more powerful and valid curriculum. And so I think here's where the correct alliances between India and the US in education amongst universities, even between industry and university, that is very important for us to do going forward.
You mentioned earlier that you developed the interest in semiconductor even during your high school.
I did.
Typically, in the Indian education system, things like chip design and semiconductors are so far only taught at a master's and PhD level, right?
Yeah.
Do you think it's the right time to introduce these subjects at the undergraduate level by basically introducing the undergraduate course in electronics and VLSI design or chip design?
I think so. I think that it's really important. So one should look, step back a little and see why not, okay? Because if you ask me the question, should you? I said, yeah, we should. Because to me, it's obvious that semiconductor design and chip design is a core competency that has to be taught earlier. Why would somebody reject it, right? And one can reject it as saying, oh, it's a more targeted education and so on and so forth, not broad-based, right? So I think that in my mind, I think it's important to build up. The answer to that question is yes, but I think what we have to do is make it a curriculum which is a little bit not only chip and VLSI design, but give people a fundamental understanding so that the person who's trained in it can learn by themselves later, so that they are not limited in their ability to learn later. They don't, even not through a master's program, but on the job learning. If you look at so many CEOs of big companies in the US, they have a bachelor's degree. They don't have a PhD, right? And why is that? Because they excelled at the job. So I think if any curriculum like that you're suggesting, I think it would be wonderful, as long as the curriculum enables the person to continuously learn. Yeah.
So I think my last and probably most important question, which is in everybody's mind, right? You said 1200 volt GaN, right?
Mm-hmm.
I think that's the battleground between GaN and silicon carbide, right?
Yes.
So do you see possibility of basically GaN going to 1700 volt and basically 2000 volt and start serving more of a like power drive type of applications in the electrical vehicle? And that will be, obviously everybody wants to know the answer about this classical battle between the two technologies.
Yeah. So I'm absolutely convinced that gallium nitride, and Transform has been a leader in this. Gallium nitride versus silicon carbide can be divided into 3 buckets. There's a less than 1 kilowatt bucket, okay, which at the low end starts from very small adapters, 25 watts, and laptop chargers, and so on and so forth. So you'll get from 25 watts to 160 watts, 240 watts, and so on and so forth. You can end up, so in the less than 1 kilowatt, gallium nitride will dominate. Okay, so there's, to the extent I don't think there'll be any silicon carbide. Now, if you go into the 1 to 10 kilowatt segment, there gallium nitride and silicon carbide could share the marketplace. I believe gallium nitride, because of its roadmap of cost and while having high reliability, that's what Transform provides for sure. Can't speak for the other players. You end up with a ability for us in gallium nitride to really dominate the segment at 650 volts up to 10 kilowatts. The 1200 volt segment was assumed to be that of silicon carbide. Gallium, what has happened is Transform has changed the narrative completely. By growing gallium nitride on sapphire, we have shown that gallium nitride on sapphire the chip has the same thermal resistance in package as say silicon carbide. It also has equal to or better performance. This, I think, has completely changed the narrative. Now, have people accepted it? No. Will people accept it? They have to, because the markets are rational. So people will try their best to say in the short term, it's going to be silicon carbide, and so on and so forth. But I believe that the rationality of the market will win. And if gallium nitride is allowed to scale in volumes, we will basically really challenge silicon carbide in the 1200 volt segment. In OBCs, I think, and I am famous for making bold and basically rash statements, but I think in the OBC segment, we will basically dominate silicon carbide at 1200 volts. In the inverter, the story has to be told. In the near term, silicon carbide, no question about it. But in 2030, what will be the market? I think it'll be shared between, even for the inverters, between silicon carbide and gallium nitride. That's my opinion.
Great. I think, thank you so much, Professor Mishra. I think we look forward to basically you contributing not just to the global compound semiconductor system, but help India also grow into this particular important technology. Really appreciate your time. Thank you so much.
Thank you very much, Satya.
Thank you.
Appreciate it. Thank you.